A direct variation is described by an equation of this form, y equals kx, where k is non-zero. K is the constant rate of change, and it's often called the constant of variation. This type of equation helps us describe situations in which two things change at the same rate. So if two things are both changing at the same rate, let's call them x and y. They might be increasing, they might be decreasing, but if their relationship is described by a direct variation, then although they both change, the ratio between the two remains the same. There are many real-world applications and examples of this. One would be a car. If you look at the amount, you might say that the amount of gas that a car uses varies directly with the numbers of miles driven. So, the amount of gas a car uses can be said to vary directly with the number of miles driven. In this case, the constant would be the mileage that the car gets, the miles per gallon of gas that the car gets. The graph of an equation described by a direct variation. The graph of an equation of the type y equals kx is a straight line which passes through the origin. K, the constant of variation, is actually the slope of this straight line. Recall that slope is the change in y over the change in x. As it says here, this is a straight line which passes through the origin. Therefore, giving you some examples of this type of graph, one may look like this, or it could look like this. So a straight line that passes through the origin. Name the constant of variation for the direct variation shown by the table. So we're given a table of values for x and y, and we're asked to name the constant of variation k. So recall that the equation in general is y equals kx, and we need to find the constant of variation, which is k, and k is the slope of the line described by this equation. So it is the change in y divided by the change in x. And therefore, we can use our different sets of x and y values to find k. Recall the slope equation, where the slope equals y2 minus y1 divided by x2 minus x1. So I'm going to choose two sets of values. It can be any two. I'm going to go ahead and choose 4 and 7 and 8 and 14. So I have my x1, x2, y1, and y2. Applying that to the equation, k equals y2, which is 14, minus y1, which is 7, divided by x2, which is 8, minus x1, which is 4. So this equals 7/4. Therefore, the answer is k, the constant of variation, equals 7/4. Now we're going to do some graphing. Example 2. Graph the direct variation given by the equation y equals negative 1/3 x. This equation is in the form y equals kx. Remember that in this case, k is the slope. So here, the slope equals negative 1/3. Recall that slope equals the change in y over the change in x. Another important piece of information is that the graph for a direct variation passes through the origin. That's very helpful because I know that I have one point already. I have the point 0, 0. I then look at the slope, and I say slope is the change in y over the change in x, and I can go ahead and rewrite this as negative 1 over 3 to make things a little bit clearer. And I know that I'm going to need to decrease y by 1 and increase x by 3 to find the next point. So I'm going to decrease y by 1, and I'm going to increase x by 3, which is going to give a point of 3, negative 1. And then I could go ahead and run a line through that and have a graph of the line described by this equation, y equals negative 1/3 x. And if I wanted to, I could find additional points by decreasing y by 1 and increasing x by 3. In the next example, if y varies directly with x, and if y equals 17 when x equals 4, find x when y equals 27. So start out by writing the general form of the equation, y equals kx. And what we're being asked to do is find x when y is 27. So let's first find k. Let's first find the constant of variation. And since we're given y equals 17 and x equals 4, what I can do is substitute those values in. So I'm going to let y equal 17, and I'm going to let x equal 4 to find the constant of variation k. To isolate k, I'm going to divide both sides by 4. Leaving me with 17 divided by 4 equals k. Now, I next need to find x when y equals 27, and I now know k. So, working right here, y equals kx when y is 27. Given that I know that k is 17 divided by 4, I can solve for x. So I am going to multiply both sides by 4 17ths to solve for x. These two will cancel out, leaving me with 4 17 times 27 equals x. And if you went ahead and did the math on this, then this actually should be 17. Let me go ahead and correct that. Then you would end up with 108 divided by 17 equals x. So x equals 108 divided by 17. And you could go ahead and figure out what the decimal is if you would like to put this in a different form, but this is the correct answer. Suppose that the distance a car travels varies directly with time driven. So varies directly with tells me that this is a direct variation. If the car travels 162 miles in 3.5 hours, write the direct variation equation, graph the equation, and find the distance traveled in 6.8 hours. So the first task is to write the direct variation equation. So the form is y equals kx. Now here we're actually talking about distance and time. So when we're talking about distance and time, we often use d and t for rate type of equations. So I'm going to use a little bit different form here. So distance equals the constant of variation times the time, or d equals kt. And in order to write the direct variation equation, I need to find k. And I have been given distance, d, and time, t. So substituting in 162 miles in 3.5 hours, I need to find k, so I'm going to divide both sides by 3.5 to get 162 divided by 3.5 equals k. And that comes out to approximately, k equals approximately 46.5. 46.3. Now that I've found the constant of variation, I can go ahead and write this as d equals 46.3 x. So I've accomplished, actually t, we're using t. So actually we have accomplished our first task. The second task is to graph the equation. Now, one thing to recall is that with the graph of a direct variation, the line will pass through the origin. And in this case, the line actually starts at the origin, the point 0, 0, because we're dealing with time, we're dealing with distance, and we're not going to go into negative time or negative distance. So we have this first point on the graph. We also know that k equals 46.3. K equals 46.3, which is the slope of this line, or the change in y over the change in x. So this means that when I go to the next point on the graph that I'm going to draw, I'm going to increase x by 1 and increase y by 46.3. So y is going to be, the y point here is going to be pretty high up. So it's going to be the point 1, 46.3. So it's going to look something like this. That is going to be the graph of this equation. Finally, I need to find the distance traveled in 6.8 hours. So I found the equation as I was asked. There should actually be an x for that equation. So k equals 46.3x. This is the equation. Or d equals 46.3t. Then find the distance traveled in 6.8 hours. Distance is what we're trying to find, and we have our equation. D equals 46.3t, and the time is given as 6.8 hours, so D equals 46.3 times 6.8. When you go ahead and multiply that out, you will find that the distance traveled in 6.8 hours is 314.8 miles. So we've accomplished all three tasks. We've found the equation, we have graphed it, and we've determined that the distance traveled in 6.8 hours would be 314.8 miles.